So here we're going to talk about the average value of a function. Now, when you hear the word average, I'm sure most people think about, averaging a finite number of numbers by adding them up and dividing by however many there are. But the word average is kind of more broad than that. It means typical, and we can talk about the average value of a function, although it's impossible for us to view it in the exact same way as we viewed other applications of the word average, because a function has an infinite number of y values, and we can't just add them all up and divide by however many there are, because there's infinity, so infinity of them. But we're going to at least start there, and that will give us the definition of the average value. And then there's a great conceptual way of understanding the average value of a function that I will show you after this. But first, let's talk about deriving the definition of the average value of a function. So what we're going to do is we're going to pretend that this function has some samples of y values that we can use. So we're going to divide this as usual. We're going to divide the x-axis up into some subintervals. Etc. We'll call that one the kth one, or the k minus first one. There's the kth one, and that'll be the nth one. And we're going to make them evenly spaced, so we're going to say that each has a distance of delta x, which is the same. Each subinterval is the same, so that's just b minus a, that distance, divided by however many subintervals we've got. And so then what we're going to do is we're going to sort of let each subinterval have a sample y value that represents it. So let's just say this here. Let's say this is, C1. I'll use blue. Let's say this is C1. So this here would be f of C1. So that point there would be C1, f of C1. And then this one here would be, let's just say we choose that guy. That point there would be C2, f of C2. Let me make this a little bigger for myself here. Etc. So then this interval we'd have, let's call that CK. So its y value would be C sub k, f of C sub k. And of course the very last one would be C sub n, f of C sub n. Now what's important is that I'm just choosing these arbitrarily. I'm just letting one of the, one x value sort of represent that subinterval, and then its y value is what we're going to use. So the point is, now I've got a finite number of y values, right? I've got f of C1, f of C2, f of C3, etc., all the way up to f of C sub n. So we know how to find the average of those guys. Let's just do it. So the average of our sample well, that's just going to be f of C1 plus f of C2 plus f of C3 all the way up to f of C sub n. And there's n of them, so to average them we just divide by n. Now, of course, the flaw in this is that this is just a finite number of y values, and the function itself has an infinite number of y values. So we're going to have to do more than just this. Let's write it in sigma notation at least. Let's call this 1 over n, and I'll add this, make this the sum of f of C sub k as k goes from 1 to n. And now what I'm going to do is I'm going to kind of utilize a little trick, because I can manipulate this and turn it into a Riemann sum, which can then be manipulated and turned into an integral. And once we have the integral, we know we've sort of made the number of subintervals go to infinity. And we're hoping that what will happen is we'll get the actual definition of the average value. So the way that works is we're going to solve this equation right here for 1 over n. So if you cross multiply and divide, you'll see that 1 over n equals change in x over b minus a. And so that we're going to make a little substitution there. Put that in here. And we're going to get, that's delta x over b minus a times that sum. And then what we're going to do is we're going to slide this delta x, since it doesn't have any subscripts on it, we can move it wherever we want. I'm going to move it right here. And now I got 1 over b minus a and so what's nice about this is if I let n go to infinity, then I'm essentially letting the number of subintervals go to infinity, and hence the number of y values go to infinity. So if you let n go to infinity, this is a Riemann sum right here, right? It's got everything we need. It's got the sum part, and it's got your small change in x. So this is a Riemann sum, which means that when you let n go to infinity, we get the integral. So this is going to be 1 over b minus a, and that becomes, in the limit, the integral from a to b of f of x dx. And this, my friends, is the definition of the average value of a function. Right? That is the average value of a function. So to get the average value of a function, you find the integral from a to b of that function, but then you divide by the length of the length of the interval, and that will give you the average value. Now, we need to talk more about this because it's a very important idea. So in the next video, I'm going to give you a conceptual understanding of the average value, which will probably make more sense than all this notation. But at least we've got the definition down, and you'll want to remember that because it's going to come up a lot.